Hi, I'm Paul, better known by my amateur radio call sign of Mike 0 November Oscar Charlie, or Monarch. Welcome to my first YouTube blog. This time I'm going to look at binary file exfiltration over DNS that I used for a HackTheBox system with a particularly stringent lockdown. After gaining blind remote code execution, we find that we can't use any form of PowerShell, certutil, or anything we upload is also blocked from running. We can, however, run MS-DOS command one-liners, nslookup, and a base64 encoder, among a few other things. However, for this demo, I'm going to use a normal Windows system, and we'll be able to see what we're doing, just so that we can understand what's happening behind the scenes, and also not to spoil the actual box for anyone that hasn't done it before. So, first things first. If we're going to do binary file exfiltration over DNS, we're going to need a DNS server. And the way we'll do that is search for one on Google and nick it, or reuse it, shall we say. It's probably more appropriate. So if we just grab that one, for example. There we go. So we have a quick look at it, see what it does. So pretty straightforward there. We'll add a few things to simplify it for us, and also, most importantly, use a proper port for DNS. So now is root. Spell it right as well. I know what we need to do. What a good start. There we go. So if we go over to our Windows box as an appropriate user, I think that one is good. Yep. Just try something. So we're going to send this to .201, which is our Kali box over here, and that works straight away, which is great. So it's also looking up both A and Quad A records, so IPv6 records, and if we scroll back we can see that it's also looking up pointer records, as you would sort of expect it to. So if we're looking at binary file exfiltration, first of all let's try simple text, well at least a crude form of ASCII exfiltration. So in both cases, as we can only use in effect MS-DOS command one-liners, we have a look at the MS-DOS command options, and the one that turns out to be quite a useful one is the for statement. So if we scroll up to here, we can see the general form. We can run a command, and then for each line we can actually put it into a variable and run some commands based on that variable in effect. Interesting options, delimiters, so by default space and tab. We can skip lines, which may turn out to be a useful thing, and the other useful thing are tokens. So we can specify a number of tokens, so that, well, where we've got a variable here, say %A, we can go up to 26 tokens, and it'll automatically name them A, or %A, %B, and so on. And another useful thing here is the asterisk. That'll turn out to be quite useful as well. And it does mention somewhere, here we are, yeah, so it confirms that here we're allowed up to 26 tokens, provided it does not declare a variable higher than Z. So we can create a crude ASCII exfil using that statement and white space. So if we, for example, do a dir, we can see that on this line we've got 1, 2, 3, 4 lines, well, 4 columns I should say, separated by space. So on this one we've got 1, 2, 3, 4, 5. So we've got a slight issue here in that we can have a variable number of columns, but we don't know how many. So we might have, for example, nslookup directory of C, and then it'll eventually go to other ones if we try all 26, which of course becomes an invalid DNS name. But let's try a few others, because they'll be useful for base64 encoded binary. If you scroll down, yeah, so it can do a // for example, which is good. Let's try plus, for example, as well. That works as well. So because even though we can specify the tokens in this form, so we can basically specify 1-26, when we're actually using the tokens, we've got to do them individually. So to avoid you watching me type the alphabet with a few extra bits, here's something I prepared earlier. So this command takes as parameter a command to run on the remote box. This is our Kali box, this is the Windows box, and we're building up a command like this. So specify tokens 1-26, got the command there, and then what we're doing here to get around this issue of the potential dots in the end is we're prepending a D. So if we've got an empty column, it just has a D. So it'll be a .d.d.d, which is going to become a valid DNS name. So what we can do on our DNS server is create something to handle all of this stuff. So let's call it DNS exfil ASCII, for example. So actually we're right at the right point here, so that's good. So because it also does A records, quad A's and pointer records, we're only really interested in the A records. So we can do something like that to specify we're only interested in the A records, and say if we're going to do something like this with these D's prepended, we need to get rid of those D's to make it more readable. So go in one, and we also get rid of the last dot, and then we replace the remaining .d characters with, say, a tab character. So you can do that with pab out. So in theory this should then convert this DNS string into ones without the D's and the dots replaced with dashes. Well, with tabs even. And just to tidy it up, we'll get rid of all the other stuff it prints out. And what we can also do is specify a static A record. So that should be matching there. So we're not going to do all this fancy stuff that the DNS server currently does. 64, so 64, dot, get rid of all that. Get rid of that print as well. Actually, that print. I'll keep that one. Keep that one. Got rid of that one. So if I've done that correctly, we should have a nice, quick, simple, and crude exfil. So we've got HMI there. So it looks like a slash is also an invalid character. Yeah. So as you notice that these two don't appear because the column ends in a dot, and therefore we're going to have dot dot D, which is an invalid character. Cool. So now we've got that, we can do some simple enumeration, and rather than just exfiltrate an arbitrary binary file, what we'll do on this demo is exfiltrate an encrypted credential, because there tend to be quite a few of these types of things all over the place on Windows boxes. And if you want to know more about this, look at Harmjoy's data protection API blog entry. So mimikatz. So the one right at the top. So of particular interest is the Active Directory one and domain backup keys, because that enables you to decrypt any of these credentials within a domain context. And there we are, it mentions it there. So excellent read. I strongly recommend you do if you haven't already. So we'll use our crude ASCII one to actually look to see if we actually have such credentials, which, as you can gather, we will for this demo. So we're going to a well-known location, and it's a hidden file. Yep. So you'll have one of these per credential, and it's an encrypted credential, which is encrypted with master key, but we'll come on to that later on. And luckily for us, it's in binary. So I've installed OpenSSL on this box, so we've got some form of base64 encoder. So if we take that file, Microsoft credentials, out cred.base64. Cool. So we've now got base64 encoded binary file, so we're going to try and exfiltrate that. So this is where we start having a slight problem. If we try and exfiltrate that line as a single token, it fails with an unspecified error. However, if we do it on Linux, it's much more helpful. It tells us why. So the label's too long. So let's quickly go to Google, DNS, name length. And right at the top, we've got our answer. Each label within a DNS name has 63 characters as a maximum length. So what's betting this is longer? Copy and paste. 64 characters. So because of the restrictions on the system that I was originally developing this for, we couldn't just do something like fold on Unix or use some PowerShell to do some fancy modification of this. We were stuck with the MS-DOS command line one-liners. So I was wondering how to extract all this, and I thought, well, what you could do is blind, again, because all this was blind, apart from obviously on a test box, we could blindly corrupt each individual line in a controlled way using the delimiter. So base64, we've got an alphabet of 64 characters plus the equal sign. So we've got a small finite set of choices that we can use, and we can basically say we've got a line like that, use the C, for example, as a delimiter, in which case that C becomes a dot, that C becomes a dot, and so on and so forth. And of course, immediately each of these tokens is now less than 64 characters, or more accurately, it's a valid DNS name. The problem comes again if we change this so that, let's say 3, change that. If we've got something like that, and say an A there as well, if we have A as a delimiter, those first 4 A's disappear, and that A becomes a single A. Or if we have, for example, 2 A's, those 2 A's will become 1 A, which is unfortunate. However, so if we take the C's as an example, I think the C's are okay with this one. Yeah. If we have that capital C as a delimiter, that is the DNS name. So we'll have 3 tokens returned to our DNS server. If we then combine them, those tokens, with the delimiter, because we know there's at least one of the delimiter between each token, we'll get a line that's equal to the 64 character length of the encoder based 64 encoded message. So because we know this OpenSSL base 64 always generates full lines of 64 characters, we know by definition that if we get a line after combining or recombining is 64 characters in length, we know what the contents of that line is. So we've in effect solved that line. So we can use that technique and in effect guessing a good choice of character to try and solve these lines. So there's a few edge cases, like if they're all A's, in which case in those cases you may have to just say, is that line all A's? But generally speaking, you should find this works. And then there's a few other things we can do as well, so we'll come on to those though, I think. So what we'll do now is we'll take our exfil ASCII, so exfil, let's call it exfil, so avoid typing. We've now got the command, but we've now got a delimiter. So what we can also do, because we know it's 64 characters and we need something that's just one less than that, is we can make use of this asterisk that I mentioned earlier. So rather than having more than 2 tokens, well, say 26 tokens, we can say up to 2 tokens, so 1 star, so 1 token plus any more after that delimiter has been used. This means that if, for example, you've got a line that, say, if you choose A as a delimiter, if the first occurrence of the A is on its own, with no A, just the character prior to it, and just after it isn't an A, that's a good A to change into a dot for the DNS name, but you might find later on along that line there's, say, an AAA, which is a bad choice. So if we can reduce the number of tokens that we create, that reduces the likelihood that we'll get a bad choice. So if we're doing this, we'll now want to say delims is our delimiter. Our tokens is now 1 star, and rather than all 26, we're going to have 2 tokens. So some choices, say if you've got say a couple of A's followed by everything else that isn't A, and use A as the delimiter, you get a valid token, but because of this star bit, the 1 star bit means there's the second token won't be, will be an empty token, so we're just going to have it on its own. So it's still worthwhile in this case having something prepended to it. So it's a balance between that and the risk of it still becoming an invalid name. So to help with automation, we're also going to add a few other things. So if we do nslookup start.delim dot, so it's a fully qualified name to the DNS server. And also within it we're going to have a marker, and this is particularly useful doing this bit. And then finally another marker, delim DNS. So this start marker and using the delimiter means that we can tell, well, the DNS server, when we encode it, will know that we have started sending a record using the delimiter as the delimiter. And then for each line we try and split it according to that delimiter up to 2 tokens. We then say we're sending a line, or attempting to send a line, and we attempt to send it. So this has 2 uses. First of all, if it's successful, we know which line it is, and secondly, we know how many lines there are, because not only do we see we're guaranteed to see a line per line, but we can also see the end point, an end marker as well, so we know when we're finished. So collectively we can use all this to in effect send the record. So let's create a DNS Xfil binary. If I can use basic Linux commands properly. So normally all this DNS server stuff is nicely concurrent, and therefore we would need to use mutexes and stuff like that if we're doing it properly. But the way we're implementing it here means that when we're actually running these commands, it's going to be sequential, because we do the nslookup and we wait for a reply before carrying on. So for this demo we won't bother with mutexes, but we will actually have some global state. So max line len, which is the maximum line length, so this is a full line using that OpenSSL base64 encoder. Have a result, so we'll store results. Let's do it in a list. Some temporary location for processing the record. So each time we get a DNS request to process, we can update this temporary record, and then when we finish we can process it in its entirety. So we can now change this. What we do now is keep the D at the start, but not replace anything. And then what we can do is take our global state of list and append the output. And then if the first 4 characters is an end dot, we've now finished sending that record, so now we can process the record. Xfil global. So that makes sense. Good. Okay, so next we'll need to actually define our function. processing record. So might as well count the lines and know what our delimiter is. So for line in exfil, and we've stored that in temp, we now process it dependent on what the line is. So it'll be 6, I think. Equals start dot. So that's the first bit. So it's that bit there. So delim therefore equal line 6. So print info using so they'll just produce some useful information whilst processing it. So we've also got an end as well as a start. So we've finished processing at this point. So it's useful to know how many lines there are. So we'll store that in a global state once we know the answer. So basically, if we don't know how many lines there are in an entire record, once we've done the first one we will, and therefore we can store that for future reference. You can also then use that as a mechanism. So even though this is some relatively quick code, it's usually a good idea to include some error checking in case either your understanding's wrong or your code's wrong. Something will go wrong and get reported, rather than go wrong and behave in a weird way that you just don't understand. Xfil and line count. Yeah. Cool. So we also have, actually no, it will be the entire line, won't it, in this case. If it equals line, because we're getting rid of the last dot, then we're just counting the line here. And because we've got a result, what we're going to do is create an array of dictionaries. So for each time we get a load of data based on a specific delimiter, we'll store that data, but we can also store if we solve it, and a few other things if we so wish. So this time it's result, isn't it? So actually, I think it's supposed to, as you can tell, not used to Python. I think it's like that, isn't it? I'm the Perl guy, you see. So yeah, so we're appending it, so we're building up an array of dictionaries. And elif line 05 data. Actually, did I include that in there? Nope, I didn't. So I've got line there, but there's a marker there, so we know it's the data. I mean, technically we can say in this particular case, if it's not anything specific, it's the general case, but we'll be specific here. So if we're at data, we've got some data to process. So again, if so, result line, and it's 0 indexed. So here we're saying that if we've already processed something with that delimiter, again we're printing out a warning. And as I say, we can also use this dictionary to store solved references as well. So in this case, if solved exists, then we know we don't have to process that line anymore. So result curline -1. So as I mentioned earlier, the way we can solve it is if we've got unique occurrences of particular characters, so as in they're not repeating consecutively. So that's a bad choice of character there, isn't it? Yeah, so for example here in this top line, all these A's, they're repeating ones, where say that J has got an R and a H in between, so that would be okay. So we'll build this up using a list. Like so. So we'll create an empty list, and then we'll go through each individual component, so each label within the DNS string, removing the D that we've added to the start, and ignoring any that are empty. So for label in line 5, so skipping the first bit, split it according to a dot. If label, so if the first part of the label is a D, we've got a valid label from our point of view, but it mustn't be just a D. If it's just a D, it's an empty component, and we're not interested in it. So now we append the label, which will be 1, because we've got a single character. So yeah, I think that's everything. So again, we'll just add a little bit here. So in this case, we've got some unexpected data item in the black area, say. So now we're at a point where we've in effect got a list of the individual components separated by the delimiter, which we don't have. So if we then combine them, we're using the delimiter as the glue. If it equals a line of length, in this case 64 characters, we're guaranteed that that's the right answer, because we know that between each individual label there's at least one of. So if obviously by only adding one you get the whole length of the string, then by definition you can't add more to any of those. So possible solution, so use the delimiter as a join, as a glue for the join. and it's dim, isn't it? So then if then pos solution equals exfil, what did I call it? 82, max line length 82, I think. We've then got a solution here. So we can print some useful information. Info solved line, go line. Should do it like that, I think. So that's a possible solution, and we'll store that in our dictionary. And then, actually, what we can do is if we also count number of solved entries as well. So perhaps do something like yep. So initialize it if it's not already there, and here we'll just increment it. And then what we'll now do is print some information about it. So we've solved exfil solved out of exfil line count lines in effect. Yeah, and return. Just return as well. So I think that is enough. So again, process all the entire record until we've got to an end. Actually, yes, there's one thing I need to do, isn't there? Exfil temp equals the empty set. Well, basically empty our temporary area. So we're not just joining it all together each time, growing bigger and bigger. So have I actually done that correctly? Oh, we've got compile errors. Oh, wow. So I've saved it as a cred.b64. So the command will be type cred.b64, and we're going to use a delimiter, in this case say of A. Let's see if it works. Nope. As usual, I keep missing those. 86. Oops. That's much better, isn't it? So as you can see, that character was a good choice for A, for line 3, 4, 5, 9. So clearly it wasn't a good choice for the first one because of all these A's here. In fact, also the second line, but also because the first one starts with an A and the second one ends with an A. So that would be a bad choice in that case. So one thing we haven't mentioned is the last line. The last line may not be a full line length. However, we're in a reasonably good situation here because our issue is that a full line is one character longer than a valid DNS label. So what we can say is that if we can send that on its own without anything else, and it gets through, it's the answer. So in this case we can use the skip option to skip all the other lines. So after the first attempt we now know how many lines there are. So after the first attempt we can say, okay, skip 14 lines and just try and send the last line as is. If it's successful into getting through, we've solved that line, even though it wasn't a complete line. So let's call it exfil last. And rather than a delimiter, we're now skipping, because we're not going to actually we can get rid of that as well, can't we? So we're now skipping, but we're not even using any tokens. Let's get rid of that. We'll have a new marker called last. And we'll still keep the end so that the DNS server, as we've encoded it, knows when it's finished with a record, because it's the end marker that does the trigger. I also need to do that, don't I? Because that may fail otherwise. So yeah, skip as our for loop option. Run the command. So we skip the first 14 lines in this case. We then try and send the last line as is. So we don't want that D either. And then we'll just send an end to then trigger the process, or the processing of that record. In fact, something else I can mention as well. We can also take that and do that. So if you've got large binary files, some of this stuff may be a bit too much for what we're doing. So what we can do instead is say and exit like that. Do something like that. So if you want to start processing much bigger files, you can then start focusing on specific lines. So if you've solved, say, 90% of it, you can just say send as a DNS request specific lines by skipping so many lines, then send that particular line. So again, you'll possibly have the tokens in here as well, which you can exercise for the reader, and then you do an end, and then you immediately exit from that attempt, or from that shell, because we're sending these as more events, aren't we? But anyway, so in this case we've got a skip. Now we're using last as a marker. So let's go back to our code and do an elif line. In this case it will be, I think, 5 again, last dot. So this time we've solved it. We will need to know the line count. So again, if we add in a bit of basic error detection, so if we do know the line, then what we can do is print again some info. Line 5, wouldn't it, in this case? And then what we can do is just take that, this, so increase the solved count and store that record as a solved record. We can also do, actually, because we're starting to get a bit more information here, least whilst we're debugging it anyway. Rep, isn't it? Xfil. I think that was it. In fact, yeah. I think that's going to be enough. But assuming I've written it right. So there's the first bit. So this is all the state that we've saved so far. And exfil last. Again, exactly the same command, but this time we're going to skip the first 14 lines to get the 15th. Oh, first time. Got that there. Which you can see matches this one here. So now we've made progress. We're at a point where the only current option is just to guess another valid character from the base 64 set of characters to find the next one that in effect will be solved via this technique. However, using set theory we can do something much better. So if we actually look at the result here, so this is the thing that's saved in the state, we've actually got the first line and the second line, and then this one's the third line, so this one's solved because it's got solved here, and so on and so forth. So there's a few lines here that we haven't got any data for. So what we can look at is a good choice of character, as we've mentioned, is one that's not repeating in any part of that line. So here, those A's would mean that A is not a good character. Here we've got an I, but it's not followed by an I. We've got an I not followed by an I. So yeah, that's going to be a good character for this one. So we can in fact create a set for that line of characters that aren't repeating, that also haven't been used yet as a test character. Then if we get the intersection between all partial solved lines of that result for each of those lines, then any character that's within that set should solve all of those lines, and hopefully any, or at least some of, the ones that we don't know any information about yet, like for instance these ones here. So this won't involve any changes on this side, it's just the DNS server. So first of all, what we'll do is we'll start with so it'll be a set. So the set of valid characters within base 64 string are numbers and the letters, as well as the uppercase ones. Plus and a forward slash. I guess technically I should add an equal sign, but I won't in this case. So if we get last line, it's solved anyway, so that's not a problem. It's these data lines, so if we're at this point, if that statement's true, we've solved it, otherwise we haven't solved it. So if we haven't solved it, we need to build up our set of duplicates. So what we can do is create a string that lists the duplicates. So for I in range 0, 2, the length of our possible solution, -1. So we look at the current character and the next character, and if they're the same, it's a bad choice of character, so it's one that's a duplicate in that particular context. Just add it to that list, well, that string in effect. and then we can quickly turn that into a set, like so. And then the good set, so the set of good choices, is in effect the set of characters that exist for that line minus the set minus dupe set, in effect. But also intersection with a set of all possible characters. So actually what we'll need to do, before I forget, is now we want to reduce that set. So if len delim equals 1, so it's a single character delimiter, because our last one, well, actually not our last one, but if we modify this in some other way, we want to make sure that we're only using one character here. Our set of characters needs to be reduced by removing the delimiter character from that set. So if we just do it like that, I think that works. So yeah, so now that good set will also exclude characters that we've already tested. So now we can say info good choice for line coline is anything from the good set. And also, because we want to look at it in a global context as well, we'll add it to our result. And the reason we'll add it to a result but not process it here is that if we've attempted multiple guesses at a choice of character, it may be a case of a specific choice, as in that last choice of character for our delimiter didn't work for some of the partial matches, so it wouldn't be matched with this data line. So by processing that bit outside this part of the code, we can make sure we get all of them. So the global good set, and this is something else that caught me out in Python. If I just set good set to exfil chars, it's actually a reference to it, so it started modifying that, which is not what we want, because it just messes things up, doesn't it? So we're interested in lines that we have partial information, so a good set, but haven't been solved, because there's no value in the ones that have now been solved. So solved not in line and good set is in line, we've got a set that is of interest. So we want the intersection of that with line, so we're line good set, wouldn't it? So we like that. In fact, what we can also do is go known unsolved, because it's an unsolved line, in which case known unsolved equals 0. If we do something like that, we can then say, actually we'll need brackets now, won't we, if we're going to do that. So solved x out of y lines with partial info on known unsolved lines and no information, whoops, on strip exfil line count. I think it, yeah, so there, line count minus exfil solved minus known unsolved lines. And also what we need is info global goods set is, so we know what good choices are. Now hopefully that's it. So yeah, I've added that to eliminate a bit there as well. So does that work? Nope. What have I done wrong there? 1, 2, 3. Yeah, of course. Yeah. So try that one first. Yeah, probably need to get rid of the debug now, won't we? It's getting a bit messy. We've got global good set there, but first thing to do now after that first line is that last line. Excellent. So now we've got partial information on 3 lines, no information on 4, but we've got a global good set here. So if we choose any of those, in theory we should solve all 3 of those lines, and may solve some of those as well. So let's try an E. Yep, solved 12 of them. So we've got 3 lines that we don't have any information on. So the global good set is now just the set of all characters we haven't tried yet. Try it plus / yay. We've now solved all the lines, or more precisely we now have the entire base 64 string. So now what we can do is do our final modification. So if len sysdarg v doesn't equal to, it's about print usage. Might as well put it in the global state. So now we'll take as parameter file name. And now also with the end we can now use that as our mechanism. So exfil solved equals exfil bracket line count. So we've solved all the lines, we've got the solution. So print info like so. So what we can also do is change that to the empty set, and let's build our base 64 string. So again, if this is a large file, you'll probably do this in chunks, but for our little demo script we won't bother. So now we go through the result. We want to make sure it's solved. So therefore it's solved, and then we'll print error. So really that's more like an insert, isn't it? And then what we say is we've got the file name in Xfil, print info, writing file name equals open Xfil file name. Right, isn't it? So open for write, and then we'll write it. So that's base64 dot base64 decode base64 struct, and then if we close that, and I think that is it. So yeah, of course. So let's see if we get our cred file. No, we don't, because we've made a mistake. Ah yes, I know what that is. At that point we need to update the global variable, not the local one, to the function. Yeah, good. So first A, I should have got rid of the debug as well, shouldn't I? Last line, E plus /, and yes, at the top here, solution found, writing cred.bin, and there we are, we have a cred.bin. So before I forget, we'll get rid of that debug now, because it looks like it might have worked. So what we'll do now is copy our cred to our mimikatz setup. And again, really good read is that Harmjoy article on what we're doing here. So we're mimikatz, and it's dpapi cred in cred.bin. So it looks like we successfully copied that binary file because it can read it, but it can't decrypt it because we need a master key. So an enterprise credential, and it tells us what our master key is as well. So it's that one there we're after. Unfortunately, all of these things are in well-known locations. So if we exit out of that, we can now go back to our ASCII version and have a look at app data roaming Microsoft Protect. And in here we'll find a directory that is the SID of the user, which is that one there. So you can also do that via, say, so like a who am I, for example, and again that works, and there's the SID again. So if we have a look at that directory, there'll be one or more files. If we just scroll down, in there as well, and we've got one master key, and then if we scroll back up, that master key happens to be that master key that we need for this credential. So for a master key may decrypt or protect a number of credentials, and you may have several master keys as well. So this is why we're doing this bit, just to correlate which ones we actually do need. So in effect you'll just nab them all if you could. So now we know that, what we can do is just go back to our binary version, and let's get our master key. But rather than run OpenSSL base64 to generate a file, what we'll do is we'll do it more dynamically, so we're not actually writing to the file system. So we should be able to do that followed by the master key. So this time, running OpenSSL base64, encode the master key. And this time, again, we'll use an 8. So we solved 4 out of 10 lines. A whole 5 lines we've got partial information on, and only 1 is missing. We don't have a global good set, but next to do anyway is that last line. And again, it's 10 lines, so we want to skip 9. Cool. So now we've got a global good set. So by removing that last line, which probably had a partial solve, means that those that are remaining, because again, in both cases we've got a full set here. So by removing that means the set of remaining lines, when you get the intersection, there is actually something there, it's not the empty set. So if we use one of those, hopefully, well, we will solve all 4 of those lines, and hopefully we'll solve him as well. So Q, let's try Q. Excellent. So we should now have our master key. Cool. So in order to decrypt a master key that's not in an active directory environment, and therefore we can't use a backup key if we manage to nab that from a domain controller, we need the SID and the password. So the first generation keys use the NTLM hash, so that's nice and easy, but the second generation ones don't. So we need to know the password or crack it. Unfortunately, again, Bleeding John has a conversion utility. So if I remember correctly, I did something like, what would it be? dpapi master key John. Yep. So yes, this synactive site has reference to it, and then you'll find it and you can download it. So let's look at these options. So first of all, SID, and then master key, which is what I've called protect.bin, and the context, it's a local account rather than a domain account. So that generates the hash that John, and fortunately Hashcat, can crack. So let's just do that. So if we copy that to our Hashcat box, then let's H over to that box, Hashcat, so yeah, there's a version 1 version and there's a version 2 version. So it's a version 2 version. So let's do that and do that as well. And I've created a smaller list of passwords so we're not hanging around too often or too much. So it does take quite a while to initialize for some reason, but then it's slow but not excessively slow in cracking it. Hopefully, I think. Yay! So that's password. So it's basically taken that master key and we've cracked it. We knew the password anyway, but obviously if you don't, and it's easily crackable. Right, so next to do is copy our master key over to our mimikatz box. SSH to our mimikatz box and run mimikatz. And now we'll use the master key option. So we need the SID again. If it's a domain one, you may have to use protected. So basically experiment. Something like the HackTheBox offshore lab I found very useful for deep diving mimikatz. So yeah, so we've got the file, the SID and the password. Excellent. So because we've got this bit here, key in the SHA-1 hash, it's managed to decrypt the master key. And mimikatz, being all helpful, has cached that. So now, also being helpful, it detects that we've cached the decrypted master key, and that master key matches the master key needed for this credential, and it should therefore decrypt the credential as well. Yay! So we've got the username, and the credential blob is the credential. So this was generated using a password generator, as you can see. So now we should be able to profit. 1056. Copy, paste. Yay! Who am I? Oh, doesn't that look good? And that's it. So apart from some of these special edge cases, like all A's, for example, this is pretty functional. And where I've been doing this manually between two parts, it doesn't take a rocket scientist to basically combine these exfil and exfil last, for example, into this script, using, for example, the global good set when it does exist, or just the set of characters that are remaining, to try and guess as a random choice which ones to use to try and solve it. And then once you've got the solution, save the solution and exit. So, not sure if this is something that's too hard or too easy for anyone, so I'd love feedback to know whether or not I should be adjusting it accordingly. And if you've got any other ideas in terms of future YouTube videos, let me know as well. And thanks for watching, and see you next time. Bye.